Okay, chemistry time. Today we're finishing our little discussion about chemical reactions, and so we're going to talk today about net ionic. That's not supposed to be one word. I don't know. That's not a mistake I usually make. This is supposed to be two words, net ionic equations in, oh fiddlesticks. I meant to have your solubility chart printed out. I'm going to pause the video in a second, but net ionic equations in double displacement reactions. Net ionic equations in double displacement reactions. Do you remember, there's another fancy name for double displacement reactions. Do you remember what it was? Maybe someone wrote it down. Double replacement. Yeah, that's not that fancy though. What did you say? Did you say double replacement? Yeah, not that fancy. They're sometimes called I think that's right, metasthesis. I think I might have spelled it wrong, but they're sometimes called metasthesis reactions. Meta meaning across, thesis having to do with the reactants themselves, and so it's just that they switch. Each one switches. Every single thing in it gets switched. I'm going to pause the video and get out some reactivity, or solubility charts so that you have those and you can use them on your test. One moment. Okay, so the reason we need a solubility chart for this is because it's all based off of solubility. We did have a chance on the last time to talk about the circumstances under which a double displacement reaction does occur. And so one of the tools we use for that is called the net ionic equation. So for instance, let's say that let's do a reaction that does occur first. Let's say we have sodium carbonate and barium chloride. They're both in aqueous solution. What does it mean if a substance is in aqueous solution? Remember, we talked about this a little bit last time. What does it mean if a substance is in aqueous solution? It's dissolved in water, and remember physically what has happened. Thank you. What does that mean has physically occurred? Like in the solution itself, the substance, which is ionically bonded in this case, because obviously if we're dealing with net and complete ionic equations, the substance is ionically bonded. But what physically happens to those ions in the water? I'll give you another hint, because water is polar. Do you remember? Let's draw a little picture. Here's some water. Water is made of H2O. H2O, what are the particles of H2O called? Yeah, what's the smallest particle of H2O called? No, it's not an atom. Water's not on the periodic table. Molecule. Yeah, they're molecules of it. So this is made of little molecules, and each one of them looks like Mickey Mouse, who I hate. Remember that? And each one of them, this is from the last chapter. Why do they look like Mickey Mouse? Because there's two hydrogens and one oxygen, and there's that shape because the oxygen has unbonded electrons. And another thing that is caused by the unbonded electrons is that each one has a little partial negative end and a partial positive end, right? Each one of them has that same, you can't see this at all in the video, but you can kind of see what I'm doing up here, right? Each water molecule has a partial positive end and a partial negative end. Yeah, right? So then when we pour in sodium carbonate, for instance, which is a sodium ion bonded to a carbonate polyatomic ion. As we're pouring them in, they're bonded. But once they get in the water, what makes it dissolve? What does the process of dissolution look like on this scale? The positive sodium ion, and really there are two of them, the positive sodium ions are torn away from the negative carbonate ion by the water. The positive end of the water, the hydrogen end, attracts the negatively charged carbonate, and the negative end of the water, the oxygen end, attracts the positively charged sodiums. And so when it gets in the water, now instead of sodium carbonate, which is bonded together, and water molecules, we end up with a water molecule bonded. It's a weak bond, but it is bonded to a sodium on one end. Each of these little waters bonds with a sodium, and each of the little waters bonds with, or some of them, and some water molecules might not bond with all the pieces, but it has been physically torn apart. That's what the process of dissolution occurs. This is called dissolution, which is the noun of the word dissolve, to dissolve. When something has dissolved, it has undergone the process of dissolution. So when this is an aqueous solution, it means that it has dissolved in water, which means it has been torn apart by the water. You can trick a dumb person. You guys know any dumb people? I usually use like second graders for examples of this because children are stupid. At least they don't know this. But you can trick a dumb person into thinking, like, you pour something in water, and like, oh, it disappeared. The salt is gone. Oh. How do you know that it's not actually gone? How does that not violate the law of conservation of mass? It tastes like salt now, and if you added the massive, like if you had a gram of salt and 50 grams of water, you would still have 51 grams together. It's just spread out in there. Interestingly, it usually does not increase the volume by as much. So even if you have, let's say, a milliliter of salt, you would not then have 51 milliliters of water. You'd probably only have like 50.3 because this tearing apart fills in the spaces between the atoms and the molecules too. Anyway, when it says it's an aqueous solution, it means that it is able to do that. If it's able to be dissolved and it is in water, it will be an aqueous solution. That's what this chart is. So look here, we have the carbonate ion on the y-axis here, and we have the sodium ion in the x-axis. Can you find where those two meet? The intersection. You draw your fingy down. Let me show you this on the screen so that people who are watching in the future, hey future people, have it. You draw your fingy down the sodium line and you draw it across the carbonate line and you end up with, what is the answer there? What does it say? Sol, which stands for, that green sol stands for soluble, meaning that it will dissolve in water. Do the same thing for barium chloride. Yeah, soluble. Soluble. So that's an aqueous solution. Okay? And now what you do to basically, and this is not yet a net ionic equation, but to basically, in the same way that for our single displacement reactions, we use the activity series to see if it does or does not occur, now we swap their partners. So now we have what instead?
Sodium chloride.
This one you don't even have to have memorized. You already know. Is this aqueous solution or solid? Is it soluble or insoluble? It's soluble. It has to be soluble because we know that sodium chloride dissolves in water. So we don't even have to look, but you can. Do look just to get better at it. Sodium chloride is soluble. So it's an aqueous solution. Plus, now look at, what's the other thing going to be? Barium carbonate. Barium carbonate. Now look at that. Barium carbonate. Insoluble. Uh-oh. So now what do we symbolize it as? Is that going to go in aqueous solution? It can't. It is a solid. What do we call a solid that comes out of a solution? Precipitate. So let's think about what this would look like. We have two things dissolved in water. They might be colored. They're not, but they might be colored, but they're both going to be clear. In this case, it would be a perfectly clear solution. It would just look like water, plus a perfectly clear solution that would look just like water. We're going to mix them together, and white chunks are going to fall out of solution. It's going to turn milky because this barium carbonate is not soluble. That tells us that the double displacement reaction did occur. Remember, if it did occur, something has to be formed here. What could be formed? I don't mean specifically. I mean what state of thing? Solid, liquid, and gas. The liquid's usually water. I've never seen any situation where it wasn't water, but solid, liquid, or gas. However, let's just do another one real quick here. If we instead had, I'm just going to do one really fast, ammonium fluoride plus sodium chloride, well, ammonium fluoride, find it. So, no,
AQ.
AQ. Sodium chloride, you already know.
Salt.
No. Sodium chloride dissolves in water, so aqueous. Switch them. Now we have ammonium chloride plus sodium fluoride. Find both of those real quick. Soluble, so AQ. Yep. Soluble, so AQ. In this case, nothing happened. We have a clear solution added to a clear solution, and what we get is a clear solution plus, because no reaction occurred. If we were to look at that on the microscopic scale, this is torn apart by the water, this is torn apart by the water, and they don't recombine to something else. They're just, all these things are just separate in the water. We don't write no reaction for it, but this is as far as it goes. It doesn't do anything. There is no net ionic equation. So that's what we're going to do next. So with this one that can have a net ionic equation, let me show you how to do it. Are you ready? So to do a complete ionic equation is the first step. Complete ionic equation. That's the first step. You make a complete ionic equation. What you do is you break everything up. Do you see why we might do that? What might be the physical reasoning why we would break these things up? Why might we break these up? Yes, they're separate, but what is the physical reasoning behind that? Why would we do that? That's what happens in real life when you dissolve them. When I add sodium carbonate to water, that's what physically happens. It gets broken into sodium and carbonate. So we just break them all up. So to me, that's the best way to remember what you do first. You just break everything up. So instead of NaCO3 or Na2CO3, we have 2 Na plus in aqueous solution. Let's talk about that. Where did this 2 come from? It was a subscript. It's now a coefficient because we're breaking everything up. Where did this plus sign come from? It's the charge. Yeah, the water has removed it from the carbonate, so now its charge is no longer satisfied by the carbonate, so it has a positive charge again. And it's an aqueous solution because this was an aqueous solution. Okay? Plus CO3, 2 minus, in aqueous solution. We keep the ions together. We don't break up this because remember, a polyatomic ion is molecularly bonded. It is covalently bonded. So even though it's involved in an ionic bond, the carbon and the 3 oxygens themselves are covalently bonded together. They don't break up. So we just write the polyatomic ion here, carbonate. Plus, split this one up? Yep. Ba, charge. Plus, try again, 2, aqueous, plus 2 Cl minus in aqueous solution. Yields, we're just bringing everything down. We're just bringing everything down and breaking it up. Break this one up? Yes or no? Yeah, we do break it up because it's an aqueous solution. So Na plus in aqueous solution plus Cl minus in aqueous solution. Break this last one up? No, why? It's a solid. It's still bonded together. Do you see the point here? Like, not only is it because this is a physical thing that we can see, but also it's a solid. The solid does not dissolve in water. So the reason we're doing this is to show how the water breaks these things up. This one doesn't break up, so we don't break it up. Does that make sense? I should have backed up a step and said, there's really 2 ways to balance this. You can either balance it like this and then move those coefficients down to this step, or you can balance it at this point. Either way is fine with me. If I were you, I would do it in the complete ionic equation step, because if you don't, you have to multiply coefficients by subscripts to get a new coefficient, which is not hard. I mean, it's basic multiplication would be like 3 times 2, but you still might as well just do it in this step. So, how many sodiums on this side? 2. Uh-oh. So, 2. Okay. Carbonates? 1, 1. We're good with that. Bariums? 1, 1. Chlorines? 2, 2. Also because, yeah, it was 1, I changed it to 2. Also because it's broken up, it's easier to balance. We don't have to worry about, we multiplied this by 2, and so we need to multiply the other thing. We just balance it in this step. Anyway, this would have, in this case, it would have balanced it. Doesn't matter. Balance it here or balance it in this step makes no difference. This is the complete ionic equation. It's called complete ionic because we've broken up everything that is ionically bonded into its constituent ions. Aye, aye? Now what we do, I'm going to write this step in red. You don't have to write this step down every time you do it, but we're going to remove spectator ions. That is a vocab word. What's a spectator ion? What's the word spectator mean? You know this from your sports. Yeah, they're just watching. They're not participating, right? If you're a spectator at a sporting event, you are not to go onto the basketball court and start hassling people. If you do, you get removed. And if you refuse to get removed, they call the police and you get removed because the spectator is supposed to just watch. So we remove the spectator ions. That is, just like an algebra problem, everything that's the same on both sides we get rid of. Bye-bye, 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 bye-bye. Can we get rid of these other things? No, because they're not the same. And then, last step, the net ionic equation. When we use the word net, even in like our personal finance, it means something minus something else. My net income is my gross income minus the taxes I had to pay. So the net ionic equation, we just rewrite it, removing the things that were removed. So we end up with Ba, I usually like to rearrange these so they're in the correct order, plus CO3 in aqueous solution yields BaCO3 solid. Yeah, this does look like a synthesis reaction. And really, because these other things were not participating, the root of this is a synthesis reaction. So this is the net ionic equation, and that is the answer. This is the answer. This is where it's very important to have the little subscripts that tell you what the state is. They're not so important the other ones. Last thing, if we did do this one, what would we find? When we got to the red step, the remove spectator ions, we'd remove everything. The reaction did not happen. Questions about net ionic equations? Okay, you have lots of practice to do. Have a good day.